Hi, my name is Eric Johnston, and I'm an aviation photographer. Join me as I document all kinds of aircraft from big to small and cool to, well, really cool. This video is proudly sponsored by Air Models. Check out their excellent variety of resin and die-cast aircraft models with over 400 commercial and military aircraft and helicopters available. Click the link in the description to see more from Air Models.
Hi there, my name is Raj Narinan, and our organization operates the Beechcraft Starship 2000 Alpha. These are two of the last 4 flying airplanes in the world, and I'm going to take you around on a walk-around tour today and give you an overview of the airplane and some of its unique characteristics, and just talk to you a little bit about what makes the Starship so unique. So the Starship, the first thing you'll notice about the Starship, it is a very unconventional airplane from the perspective of a traditional tail, wing, and another wing up in the forward part of the airplane. A lot of folks refer to this as the Canard. It's actually technically called a flying wing on the Starship, as opposed to as opposed to directional control. The forward wing actually provides lift. It provides quite a substantial amount of lift on this airplane, and it acts like a real wing. So on the Starship, you'll see a forward wing and you'll see a rear wing. What makes the Starship so unique in this configuration, just to elaborate, the designer of the airplane, Burt Rutan, was the designer of this airplane way back in the 80s when Beechcraft commissioned a project to replace the King Air. And what makes the airplane so unique, and one of the interesting handling qualities from a performance perspective, is that the airplane cannot be stalled because of the forward wing. And we'll talk a little bit later about aerodynamics, but that, in addition with a whole host of other technological advances, make the Starship a very unique airplane. So unique that was part of its demise in the market, but also very unique to the fact that a lot of people learned a lot about how these airplanes operate, some of the technology, and helped advance a lot of other airplanes that came after the Starship. So talking about the forward wing, one of the interesting things about the forward wing is that it moves. It articulates forward and in conjunction with the flaps, and the reason it does that is to help with slow speed performance. Unfortunately, on the Starship, the movement of the forward wing with the flaps is a one-cycle operation, and it's not very effective in speed reduction. It only buys you about 3 to 5 knots on touchdown, which is not a whole lot for as much as is involved with articulating the forward wing. The forward wing has also got these silver boots on it. The entire airplane is certified for known de-ice, and the way that was accomplished with achieving that requirement is to basically have pneumatic boots on the forward wing and also on the rear wing of the airplane for the Starship. And so you'll see the silver boots all around the airplane. The only difference between a silver boot and a black boot that you see on a traditional airplane is just the difference in color. So they perform the same kind of function. Some of the unique technologies that were put on the Starship was a de-ice icing sensing system. So what you're looking at here is an ice probe, and there are 3 on the airplane. And the unique thing about the Starship is they tried to automate as many systems as they possibly could to reduce pilot workload. So the ice detector on this airplane is coupled to a computer on the inside of the airplane, and it fires the boots off as needed, depending on how much ice accumulation there is, and in different order when the airplane's in icing condition. So as the pilot, I don't have to do anything other than just note that we're in icing conditions, and the boots start working as needed during that time. So that's kind of a unique system that's on the Starship. We'll take a look. We'll walk around. Starship also has the traditional angle of attack probe and a pitot-static probe. The pitot-static probe is integrated, so the static port and the pitot port are all integrated into one probe, and then of course the angle of attack indicator. I refer to these systems as big boy systems from a technology standpoint. These are the same types of systems you would see on larger Part 25 transport category airplanes. One of the interesting things about the Beech Starship is that when it was originally certified, it was not certified, RVSM requirements were not available or not around during the time And now the airplane, because of its accuracy and sensing systems, both Beechcraft Starships that we operate are RVSM certified, so we can fly all the way up to flight level 410. And that's pretty helpful with not only speed, range, performance, and fuel burn, which are really important on any airplane. So that's kind of a cool feature that the Starship systems, because they were so advanced at the time, even 30 years later, we're allowed to meet those certification rules and fly the airplane into RVSM altitudes. So here we are back again on the forward wing, and you're going to see me talk a lot about the forward wing on the Starship, because it's one of the very unique characteristics for such a large airplane to have a forward wing. And as I mentioned earlier, the forward wing on this airplane actually provides lift and also has the elevator attached to the front of the airplane. And so a very unique characteristic on this airplane is that when you articulate the yoke in the airplane, you're actually moving the elevator on the front of this wing as well as the back, as opposed to just in the back on a traditional airplane. And again, this forward wing is flying, so it's active. One of the unique characteristics about the Starship is that if you get it really slow and you get in a very, very slow condition environment, you can't stall the airplane. So it is impossible to stall the Beechcraft Starship, and the reason why is because the forward wing always loses lift first, and the airplane will drop a little bit on the nose, but the main wing, the very large main wing you see behind me, will always remain flying. So the airplane is stall proof, and that's one of the great safety characteristics about the airplane, is that you can't stall the airplane. And there is a maneuver we refer to in flying the Starship called pitch buck, and it's actually a maneuver where we allow the forward wing to stall, and we allow the airplane to sort of kind of do this wallowing maneuver and bucking maneuver while the main wing is still flying, the forward wing is stalled, and we're essentially just gradually dropping altitude, but there's no adverse conditions or pitch over or rollover movement like you'd get in a traditional airplane with the Starship, which is a great safety feature for anybody flying it, and certainly for one of the advantages of operating an airplane of this type. So Starship is a 9-passenger airplane. It's certified to a Part 23 commuter category standard. It has a lot of redundancy in its systems. The first things that you'll notice is a very, very large wing. The wing is part and parcel to the fact that the airplane can go up to 41,000 feet. So it's a very large lifting surface. More traditional wing length than you would see in a normal airplane. Again, it's a high altitude airplane. What you'll notice is that the two engines are mounted on top of the wing, very similar to the configuration in the new Honda Jet. And the main reason that was done in the original certification of the airplane was essentially to get the noise and any engine noise and propeller noise as far back and aft in the airplane so that people would not hear it in the cabin. So the unique thing about flying in the Starship is extremely quiet. All the noise is way far aft of where we're sitting. You don't have to wear headsets in the airplane, and it's quite a pleasant experience. I would say that the noise levels in this airplane are probably about the same as flying in a 737, and which makes it a very quiet airplane because of the engine mounting configuration. And what you'll notice in the engine mounting configuration is that the inlets are mounted on top of the wing, and then the engines are mounted aft, and the propeller is in a pusher configuration. And so what does that mean? That means that all the thrust is being developed aft of the airplane in a pusher environment, in a pusher configuration. Again, great for noise, and also has some really unique flying qualities that add to the kind of the effect of flying the airplane. And we'll talk a little bit about asymmetrical thrust on the Starship. We'll talk a little bit about why the engines are mounted so close together and what the advantages are of doing that. You will notice that the landing gear on the Starship is very tall. The airplane sits very proud. In typical Beechcraft form, when they designed this airplane and all the efforts that went through designing it, they overbuilt a lot of parts of this airplane, which as an operator and a pilot is great. The airplane is very robust, very overbuilt, as I call it, and all good things for an airplane that you want to fly. And 30 years later, that's one of the main reasons we operate the airplane. The other significant development in technology for the Starship that makes it so unique is the fact that Just about every structure on this airplane is composite, and it is the first certified composite airplane in the world, and it is a carbon fiber certified airplane. That brought with it a lot of advantages and also brought with it a lot of disadvantages at the time. The airplane was developed in the 80s and certified in the 80s, and at that time the certification methods and the testing capabilities and the analysis capabilities were not robust enough in the aerospace industry to be able to certify composites because we didn't understand them very well. So while Beechcraft endeavored on making the first carbon fiber airplane, and it is an all composite airplane, the cost to certify and the cost to learn a lot about the composite technology were very large in the first effort of getting this airplane certified. So there was a lot of lessons learned. There was a lot of lessons learned on behalf of the FAA, on behalf of Beechcraft, who designed and built the airplane. And 30 years later, when you look at new airplanes like the Honda Jet and 787, the Premier that Beechcraft built, and a whole host of other new airplanes, a lot of the technologies that Starship sort of figured out in the production process were used to advance those manufacturing techniques and capability to certify the airplane. And so Starship is all carbon fiber. The major advantage as an owner and an operator of this airplane is that we don't have corrosion issues on this airplane, and that is a great just a great aspect of this airplane. Most airplanes that are 20 and 30 and 40 years old have significant corrosion issues on aluminum airframes, whereas on the Starship we just don't see any corrosion, and that means that this airplane will last a very, very long time. And in fact, our first big inspection on both of our Starships showed almost no issues with the structure of the airplane, which as an owner and an operator is very reassuring given the age of the airplane. So talking about the carbon fiber airframe on this airplane, we talked about certifying a carbon fiber airplane back in the 80s and how unadvanced the aerospace testing capabilities and certification capabilities were. The advantages being that we don't see any corrosion on this airplane. That's why these airplanes look the way they are. That's why we're able to operate them 20 plus years later, because we don't have any detrimental effects to the airframe and the structure. And one of the interesting things about Starship, unlike a lot of other airplanes, it is one of the only airplanes in the world that has an unlimited life of validity. That means that this airplane, in theory, could outlast me by a factor of 5 because it's carbon fiber. And that's a pretty impressive piece, a pretty impressive accolade for this airplane to be able to have that unlimited life of validity. And in fact, a lot of these airplanes that unfortunately were scrapped during the program, when they canceled the program, that were sat out in the desert, when they were looked at 20 years later, showed no issues with the structure, showed no issues with any of the carbon fiber degrading, which makes it a great piece of technology that you can operate for a long period of time. So let's take a look. We talked a little bit about boots, and here on the main wing, which is a 50 plus wingspan wing, so that gives part of the ability for the airplane to fly at very high altitudes. What we see at the very end here is what most people would call a winglet, but what we call a tip sail. And the difference is, on a traditional airplane, you see winglets on the end of 737s and larger airplanes. This airplane has a tip sail, and the reason it's called a tip sail is because we actually have the rudder or yaw movement on this airplane is actually controlled out here on the tip sail. So the rudder actually moves, but when you move the rudder pedals, you're moving a rudder here on this tip sail and the opposing tip sail on this airplane, which is part of how you control the yaw axis on this airplane. Let's walk here to the back of the airplane. As you'll see, there's a lot of, this is the business end of the airplane. What we have here are two Pratt & Whitney PT6A 67 Alpha engines producing in excess of 1,500 horsepower each. They're rated on the Starship at about 1,200 horsepower, and they are the largest PT6 engine that's used in the industry. And one of the nice things about the Starship is the engine is still in production today. All the parts, the materials, everything to support the engines is readily available. And so we in maintaining this airplane and sustaining it, we don't see a lot of issues with the engines. The engines are relatively easy to work on. I work on the airplane myself. I do pretty much all the maintenance. We have a few folks here that help, and the engines are the easiest part of the airplane because it's the part that's readily available in the industry. And so what you have is a PT6A engine mounted here, and the exhaust of that engine is here, and then you've got a pusher propeller. These propellers are metal, and the reason you can't have a composite propeller on the back of the airplane here, or at least the time during certification, is the hot engine exhaust gases are coming out of the exhaust here, and they hit the propeller. Now that provides a significant advantage in the icing environment. As you'll notice, there is no boots on the propeller. The propeller is naturally de-iced by the exhaust gases coming out of the engine, and that provides for the de-ice functions on the propeller. The downside of that is you get a lot of carbon soot and a lot of exhaust gas residue on the propeller, which means you got to keep them clean. Aluminum propellers don't like carbon deposits due to corrosion. So the non-metallic part of the airplane here in the propeller, we have to stay on top of from a maintenance perspective, keep clean, and just watch and make sure that we have no issues with any corrosion on the propellers. Fortunately, we have a lot of extra propellers here as part of our acquisition of flying the Starship, so we can take one off, inspect it, check it out, have it serviced, and then install another one on the airplane. Because the PT6 that's mounted on the Starship, compared to, example, a King Air, is mounted in what I call the right direction, we can talk a little bit about some of the venting and cooling. Underneath here is a NACA duct, and air goes through that duct, and the oil cooler on the airplane is back here, and the exhaust for that airflow is out on this duct over here near the propeller, and that allows air to flow over the oil cooler and keep the oil relatively cool. So that ducting system basically flows through the bottom of this cowl. One of the other things that you'll have over here, you've got a heat exchanger here, so that's an exhaust grill for the heat exchanger, and you have a very large NACA duct here underneath the airplane, and that allows air to go into the condenser, into the fan and condenser for the air conditioning system. So they took advantage of every bit of real estate on the airplane to allow airflow through different systems like you would do on any other airplane to cool, to provide thermal heat exchange, to provide over here oil cooler heat exchange, and to keep all the systems of the airplane running well. You know, because this is a 1980s designed airplane, one of the things that we routinely have trouble with that you don't on modern day airplanes is environmental cooling and air conditioning. Even with all this ducting, some of the systems are older and antiquated, and so we have to learn how to maintain them and service them. And that's really the only downside I could say about Starship, is that the environmental control systems and the cooling systems on this airplane, being of 80s technology, have a few issues with some of the electronics and some of the switching. But those are things that we are pretty well understood now. We understand how to fix them and repair them and work through some of those challenges. We have an antenna here, so this is just an antenna for navigation and that's just mounted on every piece of real estate on the airplane away from things that could damage it. So probably one of the interesting things about the Starship that people will notice when you look at the business end of the airplane is that the blade tip clearance between blade to blade is roughly less than about 12 inches, which is a really interesting part of its development and really part of its flying characteristics. Having the engine so far aft and having it so close together makes the airplane extremely easy to handle and control in single engine operations, because the engines are not far out on the wing. If you lose an engine, it's very, very, very easy to fly the airplane on one engine. And I've flown both these airplanes for many hours on one engine, demonstrating different types of maneuvers. Very, very, very easy to fly because the engines are so close to what we call the center line. The closer the engine to the center line, the easier it is to control the airplane, because you don't have any asymmetric yaw conditions to tolerate. And so that's one of the advantages here of the Starship. Single engine operations with such a powerful engine, very easy to handle. And really a non-event on the airplane. So if you lose an engine or you have an engine issue, you shut the engine down, and the operation becomes very routine, and unlike other airplanes, it's not a handful to manage and to be able to fly. What we're looking at here is basically, most people look at the Starship and think it's a rudder. This is not a rudder. This device provides very little stability for the airplane, but is here purely to prevent tail strike. So if you over-rotate the airplane, you have a replaceable carbon fiber tip here. This hits the ground, and it's relatively a non-event, and it prevents the propellers from hitting the ground, which is, it's a lot easier to replace this than it is to replace an engine or a propeller. So this is really a tail strike guard, and fortunately I've never had to use it, but it's here to help protect the business end of the airplane. So when you take a look at the Starship, one of the other things that you'll see, the flap control system we talked about earlier. These are, right now they're retracted into the main wing. The flap positioning on this airplane, unlike many other airplanes, there's not multiple settings. It's either deployed or not deployed. They are linked to the forward wing, so as the forward wing swings, the flaps extend. And so that's kind of a synchronization effort. One of the disadvantages about the Starship is to develop that system and control it added a lot of weight to the airplane and also took away from its effective useful load. And that's part of the initial certification challenges that the airplane had issues with. That if you were to update or modify the airplane later on, we would try to remove that system. The flap control, the flap on this airplane and the forward wing add very little capability to the airplane, and I think was driven more because of certification requirements. And if we were to redesign the airplane, we would just remove that system altogether. It's really not required. I routinely fly the airplane without articulating the flaps or the forward wing, and it's really a non-event when flying this airplane. So what we're looking at over here is a very large, air stall fence. While the airplane doesn't stall, part of some of its initial certification requirements that the aerodynamicists wanted to make sure that they could control airflow over the wing and make sure that they could have stability handling that was positive. So we have a what's referred to, and some people refer to as a stall fence or an airflow separator divider. Same thing we have on the tip sail. We've got vortice generators, or VGs, along the tip sail, and those are there to disturb the airflow so that the rudder on each of the tip sails have positive airflow and can actually be used, and the air is disturbed there enough for them to be effective. And some of the things that, again, on an airplane of this configuration where you have a forward wing and a rear wing, that the aerodynamicists were just beginning to understand and optimizing back in the 80s, that today we would probably do without as many on the Starship. Lighting on the airplane is relatively conventional. We have wingtip lights on the end of the wing. It uses pretty traditional lighting systems that you would find on any other King Air, Piaggio, or any other airplane. We've updated some of the technology, but most of them are halogen lights on the airplane, and relatively low maintenance, easy to find, easy to replace items. So that's a good thing. The landing gear on the Beechcraft Starship is unique to the Starship. That makes it a bit of a maintenance challenge, but the landing gear has a very good long extended life limit on it. It's a very robust landing gear. It's a very simple system with one actuator and one uplock. It's very easy to overhaul the landing gear, and one of the other pieces of advanced technology on this airplane is that it has carbon brakes. So unlike other airplanes, the brakes on this airplane last a very long time, and in fact we have yet to replace a set of carbon brakes on this airplane in all the years we've been flying it. The advantages, they last forever. The disadvantages, they cost. They're very expensive. However, if you really need to stop the airplane, having carbon brakes on this airplane would make it very easy to stop, and that's a big advantage. And the reason the brakes last so long is because when we put this airplane on the runway in landing configuration, we use the propellers to actually slow the airplane down. So we really don't use a lot of brakes. Again, in typical Beechcraft form, they threw a lot of technology on this airplane, made it very capable, lots of advancements that even in this size of airplane today, you would not find carbon brakes on, but the Starship had it back in the 80s. So that's pretty cool stuff, and pretty cool technology for this airplane. So here we are in the cockpit of the Beechcraft Starship, and the first thing you'll notice is a lot of screens. And so One of the things we're going to do this morning is kind of power up the screens. I'll take you through a quick walkthrough of all the systems on the airplane and the flying end of the airplane per se. So first thing we do is check the external power, and that looks good. We'll turn the battery switch on. We bring the external power online. And we'll turn on all the avionics. So even though the Starship is almost 30 years old, one of the first things you'll notice is that we've got 16 CRTs, and so these are cathode ray tubes. Very early technology. There's no LCD screens here. Each one of these screens is actually really a small TV. That was the first generation Collins avionics system, and this system is still used on some of the later generation airplanes, although they've mostly phased them out now into LCD screens and LCD technology like you would see with a Garmin system or you would see with an Avidyne system. And so what we do when we power up the screens, the first thing that you're seeing, you'll see a sign here that says AHRS aligning, do not taxi. So that's the attitude heading reference system on the Starship, and that's the computer that's basically trying to figure out the stability of the airplane, and that's electronic. So those are warming up, and those are getting all calibrated, and that takes a few minutes when you start the airplane, start the avionics on the airplane. One of the great things about the Starship that most people don't know is that while this airplane is a 15,000 pound gross weight airplane, which means it's certified over 12.5, it requires 2 people to fly this airplane. However, the Starship has a single pilot type rating and can be flown single pilot, which is the way I fly the airplane, which means that most everything on the cockpit end of it has to be very well automated. And I'll take you on a quick tour, of that automation. The first thing we do when we power everything up is we go to the checklist. And one of the nice things about the Starship is that it's got a digital checklist. It'll take a second here to warm up. And what you'll see on the checklist is, like you would see on any other checklist, all the items that I would have to go through and clear before I start the engines and or start traditional flight operations. And and because this is a single pilot certified airplane, I can do and maneuver down the checklist right off of the yoke. So I don't have to push any buttons here. I do everything by pushing a button here on the yoke, and I can scroll down all the systems and check them before we go start engines and start doing other parts of the checklist. The nice thing about this checklist is that it has the normal procedures, it has abnormal procedures, the radar screen, and it also has FMS status for the flight management system. And one of the really cool things about the Beechcraft Starship avionics system is that I can look at any issues on the airplane, any possible problems with the airplane. I can look at it and figure out what's going on. And I currently have 2 open squawks on the airplane, which are probably older squawks that have been rectified, and I can determine if the DME distance measuring equipment or the altitude display is having an issue. Everything seems to be functioning, so for right now, those are just alert messages that I need to deal with. Starship was also certified with ICAS. ICAS stands for Engine Instrument Crew Advisory System, and what you see here is engine health and engine performance. What you have here on the top is the ITT, which is the turbine temperature, the propeller RPM, the N1 on the turbine, and then you have oil pressure and fuel flow. And so all that can be monitored here on Starship, and all the messages that are in yellow are messages for systems that have an issue, and because the airplane is not actually turned on, you would expect to see all these messages. As we get fired up and get ready to run the airplane, those messages would disappear. But I can manage the health of the Starship and all the systems on the airplane from this one screen, which is another significant technological advancement than at the time compared to other airplanes that were more steam gauge driven and traditional instruments. I can look at everything on this airplane and in about 5 seconds figure out what's working well and what's not, and then what do I need to do to address it. So with the 16 CRTs on the Starship, The reason there are so many CRTs was for redundancy. Again, this is a single pilot, type-rated, certified airplane, and to be able to do that, I've got to have lots of backup and lots of redundancy. Starship has the capability here on the primary flight display and the multifunction display. I have the ability to move displays from the bottom to the top and from the top to the bottom. So I can pretty much send signals and data to any one of these screens in case I lose a screen or lose a computer. And that's a really great backup safety feature as part of the Starship. You know, I often tell people when they buy airplanes, you're not really buying performance as much as you're buying safety. You're buying levels of safety. And the main reason I fly the Starship is in this category of this airplane size, it's one of the safest airplanes in the world because of all this redundant technology, which makes it easy to fly. And if you have an issue, and I've had issues on my flight, maintenance issues, you can change and move data to different systems and continue your flight without being in a situation you don't want to be in. So that's how the displays can be moved around. The other thing that can be done is the central display unit here, called the CDU, is where I input all my nav comm frequencies. So you see COM 1, COM 2, nav 1, nav 2, my flight plan. I can put in all my FMS waypoints right into the CDU, and that's a huge easy keypad to drive. And if I lose the CDU, or if I lose my comm page, Starship has a backup system over here. I can come over here and I can use the comm right here on the radio tuning unit as a backup. So that's another backup to this system to be able to dial frequencies in. Starship has two NavCom receivers and has pretty much two of everything from a navigation and communications perspective. I can also move data from the engines down to the RTU. So if I lose the ICAS screen, I can move engine data into the RTU and fly the airplane off of the RTU screen for engine data, which is a really cool, again, backup feature and part of the safety part of this airplane. And if I lose the ICAS page and my screen here is working, I can do a reversionary ICAS mode, and I can move the engine instrument information down to the bottom screen and vice versa. And then the last part of the redundancy element of the avionics system is the fact that what's exactly displayed here for the pilot on the left side is duplicated for the co-pilot on the right side, so I can fly the airplane from the left or the right side. It's really up to me, depending on how I want to fly the airplane. So let's take a brief tour of some of the systems on the airplane. We talked about icing systems earlier. This is the ice panel page. It controls all the external heat and the icing systems. Again, it's all automated. Once I turn it on, I set it, I forget it, and I don't have to worry about this panel and operations for the rest of the flight. Over here, I have a comm panel. It's duplicated on the co-pilot side, and this is where I can basically adjust all the volume, radios, and drive different types of communications into my headset or into the outside audio speaker. This is the airspeed indicator. It's a digital airspeed indicator, and this is the sensor display unit, which is a backup to the nav page. It'll show me VOR, ADF, and DME information. It's a backup system. It's cross-linked to the right generator on this airplane, and then the co-pilot side is cross-linked to the left generator, again as a redundant backup. Primary flight display, multifunction display, altitude indicator, CDU, ICAS, engine instrument crew advisory system. This is my checklist page. It also drives my weather radar. Starship has an advanced radar system on board, and that information can be displayed here, or it can be displayed here on the multifunction display. We'll in fact just turn it on really quickly. And you'll see the radar page. Gets dialed up, and we're not seeing anything in front of us, so we'll go back to standby on the radar page. We talked about the RTUs. These are backups to be able to dial communication frequencies. These are my standby pack instruments. If I lose all the avionics on the airplane, I'll be able to fly the airplane with my airspeed indicator, my standby attitude indicator, and my altitude indicator. And then everything again is duplicated on the right side of the airplane as a carbon copy of the left side of the airplane. Down here in the center stack, what I have here is fuel. So I have fuel on the left and right side. I have electrical power across all the bus systems. Starship has a left generator, a right generator, a center bus, a triple fed bus, and this will tell me the health of all the electrical systems on the airplane. And these are the ignition switches here to start the engines. Down here is a pretty traditional stack of controls for throttle, prop, and fuel. Very similar to what you would see in a King Air. Pretty much the same type of setup. Starship is not a FADEC airplane, so it is a mechanically linked airplane for all the engines. So when I move the throttle levers, I'm actually moving a cable that's moving the fuel control lever on the engine to actually drive more fuel into the engine. Newer airplanes now have gone to electronic. Starship is still mechanical in that regard, and I quite like the mechanical linkage because I know that I'm driving a mechanical linkage on the engine, and that's a great feature for me. I'm comfortable with that technology. Down here is autopilot. Starship has a digital autopilot system, one of the most advanced digital autopilots made by Collins, and in fact you have to have the autopilot to fly at single pilot, and we control the autopilot through all the digital servos and technology right out of this panel here, and including the flight director display unit here, which tells us exactly what mode we want from a navigation, heading mode, vertical speed mode is all driven and coupled to the autopilot from these two panels here. So it's a very automated airplane for a 1980s design airplane, and in fact even in comparison to today's airplanes, it's a pretty automated system that allows one pilot to be able to fly a fast, high technology airplane such as the Starship and manage everything in the cockpit very effectively, very safely, and very efficiently, with all these systems and technologies. So we're in the back end, or the passenger compartment of the Starship, and what you'll see here is 6 seats. It's a very comfortable airplane. It's not a full stand-up cabin, but it has a trench, as I call it, so you can pretty much stand up in the airplane if you're about 5'10" or under. The seats are very comfortable. They articulate in all directions. Very, very quiet in this cabin, as we talked about earlier. We have a belted potty in the back, so we do have an onboard potty slash lav, and that also functions as a seat. And then in the very back of the airplane is the storage. All the storage for the Starship is done internally, so we can't store anything on the outside of the airplane. We store everything on the inside of the airplane. And the cabin with a full load of fuel, 6 people and 1 crew. The airplane, it's no problem flying the airplane from a gross takeoff weight perspective, and in fact routinely we have 6 or 7 people on board, full fuel. From Dallas we can make it to pretty much anywhere on the West Coast, anywhere on the East Coast, and the Northwest is a one-stop trip, which makes the range and capability of the Starship very advantageous for our business operations here out of the Metroplex. So the interior on this airplane is mostly original. We've redone a few little pieces here and there. We keep a lot of spares on hand, so we have a lot of capability to be able to redo seats and things like that. But it's a very, very comfortable cabin, and again, because the engines are mounted so far aft, you can't even see the engines from the seats here in the cabin. You can barely see the engines from the seats in the cabin, but the noise is all behind you. Makes it a very quiet, comfortable experience to fly in.